Okay, so I'm going to be talking about friction. I'll start off by reading the definition of friction. It's a force that resists the movement between two contacting surfaces that slide relative to one another. So I'm going to show this with a diagram. So let's say we have this box. Alright, we have this box that is along this surface. This is not a smooth surface. It's a rough surface. So, we are then given this, that there is a weight to this box, our weight, and it is also being pulled this way with the force of P. So, what this is going to do is, since this is not a perfectly smooth surface, it's a rough surface, there's going to be friction right here. So this frictional force is just going to be applied to the bottom of this box. The force is just acting between the surface and the bottom of the box. And we can say that is going to it's going to be equal to the change in the frictional force, since the box is being pulled along an uneven surface. The surface is not going to be it's not going to apply the same amount of friction to each point in the box the entire time it's being pulled. So like this side might be getting more friction than this side, and then as it's being pulled, it's just getting different frictions in different places. So that's just why we call it the change in F, the change in the frictional force. And along with this, there's also going to be this force called the normal force, that is going to be kind of the same idea as what I just described in this frictional force. It's going to be kind of a distributed load. Let me show it like this. It's going to be distributed load because this surface is going to be uneven. Just like that, it's going to be uneven. So in every spot, it's going to be applying a different amount of force back up onto this box to counter this weight of the box. And it's going to be the normal force with N, but we're going to call it the change in the force of N to show that it's uneven, really. Okay, sorry, I had to plug my laptop in. Now that we have that, I'm going to kind of make this diagram on a little bit bigger of a scale so we can see some more details for it. Alright, so we have this box again. It's along this uneven surface, non-smooth surface. Oh man, this marker. Okay. And right now, we're going to be looking at it in the case that it is in equilibrium. That is the weight of the box working with the force it's being pulled at, the frictional force, and the normal force. We're going to say they're all in equilibrium. So in this case, it's not going to be a distributed load. We can narrow it down to one point, or we can find the resultant normal force. So we can just say that's right here somewhere. So we broke it down into little simpler terms since it's in equilibrium now. And with this, in order to solve this, we can find, or in order to get an equation from this, to find this normal force and the frictional force, we can do this. So that's our W, that's our line of action for W, and we have this length right here being X, and this height that the force is applied on the box, H, above the ground. So in order to find this, to give a formula for this, rather, we can have this formula, Wx is going to be equal to PH. So the weight of the box times the distance it is away from the normal force is going to be equal to the force it's pulled by times the height above the ground. Yeah, so what this basically means, since it's in equilibrium, this frictional force is going to be really equal to this pulled force, and same with this normal force is going to be equal to the weight of the box. And since we just also multiply it by the distance it is away from its line of action. So you can manipulate this formula down in any way to find whatever force or number we don't have for it. But that's just how you set it up. So doing this is going to give us a resultant force between this F and N right here. It's going to produce a resultant force, and we also are going to end up with this angle. Okay, I got a little ahead of myself. This resultant force and this angle, I forgot to say, this is going to be in the case where we're dealing with impending motion. So that's basically just, we can get two formula, that's when the actual pulling can overcome, and it won't be in equilibrium anymore, and it will be moving along this this surface right here. So that's going to end up giving us a formula to find this frictional force. It's going to be, the frictional force is equal to mu times the normal force. So mu in this case is this coefficient in math is usually known as the static coefficient of force. So we can use this formula to find frictional force or normal force in this situation. Or we can use it to find the, if we have all those values, we can use it to find the coefficient of static force. Or sorry, the coefficient of static friction. And also we have a formula right here to find this angle. I'll write this down here. That is going to be equal to, well, we'll do it this way. The tangent, can you see that? I might do this in a different color. So in order to find this angle, we have the tangent of that angle is going to be equal to the normal force over, because this normal force can also be shown right here. So it's going to be the normal force, or I'm sorry, the frictional force over the normal force. So just like that. It'll be static friction. So we were able to move this to the other side, so it could be the angle is equal to the inverse tangent of the static frictional force over the normal force. But we'll break this down further, given this formula right here, since that's static. Both of those are the static frictional force. We can say that this angle is equal to the inverse tangent of mu times normal force over normal force, substituting in that formula. So we're going to bring this back over here. I'm running out of room over there, so I'm just going to make this all equal. So basically, what all this is, so we can take out both of these. The angle in this situation is going to be equal to the negative, or the inverse tangent of the coefficient of static friction. So these are just some formulas we can use to find different variables in a problem dealing with friction, in equilibrium, and in impending motion.